Hi, welcome to another edition of Linear Algebra. Today we are going to take a look at section 2.2, direct methods for solving linear equations or linear systems. So in the last lecture we gave a general overview of what's going to happen, and today we are going to get into the details of how we are going to solve linear systems. Let's go ahead and take a look at the program for today. So we are going to have a long list of basic ideas to talk about, and I thought perhaps the best thing to do is to start with an example, and while we are solving this linear system, I'll be explaining the topics for this section. So you remember that the matrices came out of applications of various physical law. When we write the matrices, when we write the systems, we have a linear system as you see here. So we make sure that our variables are lined up, so x, y, z, u, w, and this is our right hand side. You noticed one of the first things that we said we are going to encounter is some sort of a culture shock with just so much data to deal with. So right here you see 24 numbers to be handled. So we at the beginning try to save some time and some writing by just not writing the names of variables because they really don't do much. So we're just extracting the numbers. Of course, for that to work, we have to have x's lined up and then y's and so on. And we have to remember what each of these coefficients are coefficients of. So this was for y, x, y, z, u. This was w, and this was, of course, our right-hand side. This left side, this is referred to as a coefficient matrix. The right one, of course, the right hand side vector or matrix. The whole thing is referred to as augmented matrix. Okay, now down to nitty-gritty detail. How do we find x, y, and z and so on? You remember last time we started with some simple examples. Let's take a look at that and see what made it so easy. So easy to solve systems were triangular systems, which we solved by back substitution. So here's a triangular format. We said we come to the least crowded one, solve that for z, put it in the previous equation, that's why it's called back substitution, and then find y, and then put both of them in the previous equation and find x, and we are all done. So triangular system where time saver, here's a triangle, we are referring to zeros down here, or the system of equation here itself up here. So you can look at like two triangles we have, and then we said if we come across problems that are not that straightforward, the idea would be to actually try to make it triangular. The method that we use to do this thing was called elimination method or Gaussian elimination. So if we came across a problem that was full matrix, then we aim at eliminating some of these entries so that it'll be a triangle one. Well, every now and then when we attempt to do this thing, we don't get a perfect triangle and we get something else. The next best thing is called the echelon form. So echelon form is kind of like a, if you wish to call it, a crooked triangle. It's not like a perfect triangle that you want, but it's the next best thing. So next idea that's coming up as a generalization of this triangular system is going to be called echelon form. So we are going to we aim for triangular. If it is like that, that's great, but typically we come across a row echelon form. Let's go ahead and talk about what the echelon form is supposed to be. So given given this linear system, we try to eliminate some of these entries in a particular style, and in the process, instead of coming with a triangular form, we might end up with something else. Here we can see that it cannot be triangular because, well, I have 4 rows here and 5 columns here, and something is not going to quite work out. So let's go ahead and take a look at a variety of echelon forms, see what is an echelon form. So here I have so we have the idea that we want to deal with these big systems. This is another example. It's a 6 by 6, but let's go take a look at the echelon form. So in explaining echelon form, down here you see some zeros. These squares are supposed to be non-zero entry, and these star entries, they could be any number, 0 or non-zero, we don't really care. A matrix is going to be in echelon form if there are any rows of entire zeros, they have to be at the bottom. So for example, here you see an entire row is 0. This one has 2 rows of zeros. Aside from that, this is referred to as a leading entry, or the first non-zero of a row. It has to occur to the right of the leading entry above it. So each leading entry is to the right of the leading entry above it. Now it doesn't have to be exactly to the right of it. This one, for example, is 2 steps to the right. This is another echelon form. You see here is a non-zero entry, whatever it is. Then the next one shows up here, and the next one shows up over there. This one at the beginning looks like a perfect triangle that I have the first non-zero entry here, next non-zero entry, next non-zero entry. The last one happens to be entire rows of zeros. Here are some other examples of echelon matrices. This is also row echelon form. This is again in this file. These are non-zero entries. As we said, the rows that are entirely made of the zeros have to be at the bottom, and then the non-zero entries have to have a kind of a staircase style, except that doesn't have to be a perfect looking staircase. So for example, here you see that I have a non-zero entry here. The next one shows up 2 to the right, the next one 1 to the right, the next one is showing 3 to the right, the one after that right after that to the right. So that's the idea of an echelon form. So that's the next best thing to a triangular form we are trying to produce. Once we have our matrix reduced in that style, we are done with half of our task. That is, you remember, if I go ahead and eliminate entries at the bottom, so I get that triangular or row echelon form, then, well, I'll be dealing with that kind of a triangular form, and then I can solve it with back substitution, perhaps with some additional steps that we are going to talk about. So let's go ahead and see what we do here. So first we write our matrix in this style so that we don't write the x, y, z's anymore. Next, we need a little bit of a terminology. So when we are talking about elimination, we have a clear language for it. I'm going to refer to this as my pivot, and I'm going to refer to these numbers below it as targets. So I'm going to use my elimination method to get rid of my target. Well, how would you get rid of this 2x? Simple idea would be to multiply this equation by -2 and add it to this equation. Well, this is representing those equations for us, and we might as well say what I'm going to do here is multiply the row 1 with -2, so I write -2 row 1, and then I add it to row 2. So -2 row 1 added to row 2 is going to eliminate this 2 here. While we are doing that, we might as well do row number 3 as well. So -2 row 1, this case happens to be the same number, and then I add this to row number 3. How would I get rid of -1? If I simply add row 1 to row 3, then I'm done. So I can just take R1 as it is, add it to row 4, and that's going to take care of it. So once we are doing these things, you have an option of writing the -2 R1 somewhere and add it to this, but hopefully you can do it in your mind and do that also, of course, carefully. So what's going to survive after we have done that? Let's go ahead and write our next matrix. So first the row stays as it is, even though we're talking about multiplying it by one number or another. We just leave it intact. So -2 times 1 plus 2 is going to be 0. -2 times 2 plus 4 also. This one, our aim was to get rid of this, but that one also dropped out. -2 times -4 plus 0 becomes 8, and there's another 8 here. -2 times 5 is -10, and this becomes -8, and next one, -2 times 1 plus 2 is going to get 0. Same thing for this one. So let's go ahead and write that. I want you to do this thing in your mind or on a piece of paper, and so go ahead and carry out these 2 steps. So here's our break. So you go ahead and do that and come back and make sure you follow the steps. So I do the next one. So I'm going to get 0. This is going to be -2 times 2 is -4 plus 3. It's -1. Next one is 10, 9, -5, -1. When I add them, I get 0, 3, -1, -2. What's that? 10, 27. Is that right? Yes, I made a mistake here. This was supposed to be, I'm adding -4 and 6. That's supposed to be +2. So let's correct that before. That's one of the dangers here, that one mistake and we are actually going to be in trouble. We'll talk about how to get around that issue later on, but let's proceed. So I aimed for these targets, and I achieved that by making this is called the sub-column. This sub-column has become entirely zeros. Now what happens is that for the time being, our first row and first column are kind of out of commission. That for a while we are not going to have much to say or do with this section of the first row and the first column that are going to be out, and then we are going to concentrate on this so-called sub-matrix. So we have an idea of a sub-matrix. Let me write the words for this one. But this was our pivot, and this was our target. These are our targets, and then we have a multiplier that we use to actually eliminate our target. Okay, now we come here. We want to use somebody as a pivot and everybody else as a target. Of course, I can never use 0 as a pivot, because any multiple of it you add to anybody else, it doesn't make any difference. So this cannot play the role of the pivot. one of the other ones has to play the role of the pivot. Now, which one do you want to use as a pivot? That's a separate discussion. That is actually a very important discussion. But right now, for hand calculation on these small problems, the easy thing for us is to use the small number as our pivot, just simply because our arithmetic is a little bit less tedious if we do like that. Later on, we are going to say, as a matter of safety, larger numbers are better, but for now it doesn't matter, and we go with the smaller number. So the next thing we are going to say is that we like to see our pivots in the so-called diagonal position, or just simply for our convenience, we are going to take this and swap it with that one. But we cannot just swap two numbers like this. We have to swap the entire rows. What does that mean? It simply means taking your equations and writing it in a different order. So it's not a major mathematical operation or anything, just reshuffling how you write your equation. Like this was equation 1, 2, 3, 4. We are exchanging the location of 2 and 3. So this operation is referred to exchange operation. So R2 and R3 are going to swap their places. Nothing else is going to happen. Again, just because we like to see our pivots to sit on a sequence that looks like the position on that triangular setup. So the main operation that we had here, you see one operation here, multiplying a row with a number and adding to another row. We call that addition operation, even though it's a lot more complicated than that. That's the meat of the whole process, is that the main idea is buried inside of this. The other ones just for convenience to make things look nicer. So this one we are going to call it several names for it. One is the exchange operation. This is exchange. You can call it a swapping or shuffling, or any other word that you want to add to it. This one we are going to call it the addition operation. Okay, when we exchange these two, what happens? Well, unfortunately we have to rewrite this thing all over again. So 1, 2, minus 4, minus 4, 5, 1. And then we are going to write this 0, minus 1, 10, 9, minus 5, minus 1. And the other one comes down 0, 0, 8, 8, minus 8, and 0. And then we have again 3, minus 1. Excuse me. Made a mistake. This is 0, 3, minus 1, 2, 10, 27. Okay, so we wrote all of this thing just because we swapped, but let's go on. So now we say, okay, we are gonna again, let me just emphasize for a while that this section of the matrix for a while is going to be out of commission. We are going to take this minus 1 as our new pivot, and well, 0 is 0. We don't need to do anything to it. So this is going to be our target again. So this is a pivot, and that's our target. So this is our pivot, and this is our target. Well, how do I get rid of the target? Again, we come back to this major operation here. Again, let me ask you, what should I write here? This is a command. This command is acting on this matrix, and out comes the next entry. What should I write here for my next operation? So if you said 3 times what? 3 times R, what is my subscript here? This is of course R2. So R2 refers to our current R2, not the original one. So whatever the current set of number is called R2. And we are taking that and what? We're adding to R4. Again, there was nothing for this one to do. We are doing another addition operation. Out comes Uh, well, here is, we said the curse of dimensionality. We have to write plenty when we are doing this. So 0, minus 1, 10, 9, minus 5, minus 1, 0, 0, 8, 8, minus 8, 0, and then I have 0, 3 times minus 1, and this is going to be, of course, 0. That's what we want. 3 times 10 and minus 1, so here's a not so nice looking number, 3, 29 again. 3 times this is going to be minus 15, so minus 5, and this is going to be 24. Okay, by now, for the time being, we had the idea of this pivot and these were targets, so we did that. Then this was the pivot and these guys were the target, and we took care of that. Once we are done with those things, the two rows and columns are temporarily out of commission, and we are focusing on the next submatrix. So in the next submatrix, I have to use 8 to eliminate 29. So again, this is our next pivot, and this is going to be our next target. What should I do here to do this? When it comes to these problems, you have some choices. Sometimes you can reorder things a little bit. For example, here you can do one of two things. If I take row 3, okay, divided by 8, multiply by 29, and make it negative, take minus 29 eighth of row 3 and add it to row 4, what's going to happen? Well, when you divide this thing by 8, this becomes 1. Multiplied by 29, it becomes 29. Make it a negative, it becomes negative 29, and that is going to cancel this. So 3 operations. You can do it like this. Sometimes some students prefer to do this thing step by step. Especially here, I see all of my numbers are multiples of 8, so I might as well, instead of doing this, I might take this row as simply divide it by 8, so that my pivot becomes 1. When 1 is a pivot, life is a lot easier than if it is anything else. So if you wish, you can just divide it by 8. Of course, the drawback is that we have to write this thing all over again. So I have 1, 2, minus 4, 5, 1, and 0, minus 1, 10, 9, minus 5, minus 1, 0, 0. Now this becomes 1, 1, minus 8, excuse me. Of course, that's also divided, all of them divided, 0. And this is 0, 0. This is still 29, 29, minus 5, and 24. Okay, so we did this operation. Just multiply a row by a number. So it's called multiplication operation. So again, let's review. We have 3 types of operation. This is called addition, this is called exchange, and this is called multiplication. The real operation, the meat of the whole thing, is this. These two are kind of cosmetic steps. So, okay, if you divide by 8, now you can think about this a lot easier. If this is 1 and you want to use it to target 29, well, let's go ahead and do that. So how do I do this? I said now to minus 29 R3, if I add R4 to it, then I'll be done. So let's go ahead and do that and write one more time. 1, 2, minus 4, 5, 1, 0, minus 1, 10, 9, minus 5, minus 1. This was 0, 0, 1, 1, minus 1 0, and 29 times that becomes 0 0, this becomes 0, this becomes 0 again, and now we have another accidental 0 here, and this becomes 24. Is that right? This becomes 24, and well, this was already 24. Okay, what now? Now we have achieved our echelon form. So here is the crucial thing. Let me draw this. We have, these are our leading entries, minus 1, minus 1, this 1 here, and this 24. You see that each leading entry is to the right of the one above it, and that makes it echelon form. We don't have a row of entire zeros here, so what we have is an echelon. So look at the zeros, see how they look like. Here's a stair, here is another stair, and this one, instead of dropping right away, it goes a little bit extra and then it drops. So this is indication that we have achieved a row echelon form. This is a row echelon form. Okay, now we have an option. We want to solve and find x, y, z, what was the variables, u and w, I guess. I didn't call it a v because u and v look like each other. It causes a problem. U and w. So x, y, z, u, w, we want to go ahead and find them. We can do it by back substitution, or we can do it by Gauss-Jordan method. I prefer Gauss-Jordan because, well, it's the same style that we have been doing. It looks a lot cleaner. And so two options. One is the back substitution, and the other one is the Gauss-Jordan. Style. So remember, back substitution was find the last variable from here, go to the previous one, go to the previous one, go to the previous one. That was the back substitution. But that back substitution that we want to do essentially boils down to eliminating some of these entries above here. So why not go ahead and eliminate them first and then solve? And that's what the idea of Gauss-Jordan is. So Gauss-Jordan says, well, let's go ahead and start to clean up and eliminate. Here we benefit by simplifying this. Again, I take my row number 4, I divide it by 24 because life is going to be a lot easier if our pivots are 1. So we are going to give a name to that later on, but right now we just divide by 24 because this equation reads 24 w equal to 24. You would have divided it by 24 anyway, and that's what this thing tells us to do. So let's go ahead, write one more line. 1, 2, minus 4, 5, 1, 0, minus 1, 10, 9, minus 5, minus 1, 0, 0, 1, 1, minus 1, 0, 0, 0, 0, 0, 1, 1. So this, the last equation here, if you go back and write it in the traditional format, this one really is telling us w is equal to 1. This thing is really saying w is equal to 1. This one is x, y, z. So that's really z plus u minus w equal to 0. And so on. Each of these things representative of some equation. Now we say, okay, the next guy is going to be, our pivot is going to be this. Well, there's nothing below this thing to do anything. So what do we do with it? We take that and eliminate entries above it. That would be essentially finding w equal to 1, placing it in the previous equation, and trying to bring it to the other side. So we are going to use this as our pivot, and these are going to be our targets. So let's go ahead, let me make room for that. And so how would I handle this? I take R4 and add it to R3. Now this is going to be quite painless because these are all zeros. We don't have to do really anything. This is going to reduce this thing to 0. How about here? Going to be 5 row 4 plus row 2. How about here? Minus 5 row 4 is going to be added to row 1. So those are the operations that we are going to carry out. Let's see what's going to be left. We are going to have 1, 2, minus 4, minus 4, and next I'm going to have of course 0. 5 of this is added to that. Minus 5 times 1 plus 1 is going to become minus 4. Next row we are going to have 0, minus 1, 10, 9, 0, and 4. So this is supposed to become 0, and 1 times 5 plus minus 1 is going to become 4. Next row I have 0, 0, 1, 1, 0, 1, and last row is going to be 0, 0, 0, 0, 1, 1. Okay, what is next? Here comes the crucial distinction. Our pivots are the following entries. And this was a pivot, this is a pivot, this is a pivot, and this is a pivot. Okay, first non-zero entry of each row, these are our pivots. Crucial thing is that this is not a pivot. You cannot use this thing to eliminate these entries, because what happens is that you're going to destroy the other formats you have created. So if you try to add this to that, then you're going to lose the control of this one. So what we do is that we are going to take this one and eliminate the 10 above it. So we are going to take that and eliminate this 10 and this minus 4. So the last pivot here, we use the entries above it. Next pivot, we are going to use that to reduce the entries above that, and after that it's going to be time for this one. This is going to be our next pivot that's going to be used to remove the entries above that one. So what do we get in this case now? We are going to get, so I'm going to write minus 10 row 3 plus row 2 and 4 row 3 plus row 1. As a result comes 1, 2, 0, so 1, 2, 0, and so I'm multiplying this thing by 4 and adding to this. This turns this into 0. 4 times 1 and a 1, that also becomes 0 accidentally. This is 0 and 0, so I just get a 0. 4 times 1 and add it to minus 4, that also, so lots of accidental zeros. Minus 10 times this, so I have 0, minus 1, this becomes 0, this becomes -1, this becomes 0, this added that becomes -6, and I have 0, 0, 1, 1, 0, 1, and last rows are stay as they were. What is next? Next one is, this is our pivot and this is our target. So notice what happened. We cleaned stuff below, we are cleaning stuff above, except that certain entries are not pivots and items above them cannot be cleaned. We are going to see what we are going to do with them shortly. So how do I get rid of 2? Of course, I'm going to do twice row, it's supposed to be red, twice row 2 and add it to row 1. What comes out of this? Let's write it. I'll have 1, 0, 0, -2, 0, -12, 0, 1, -1 now, 0, -1, 0, -6, 0, 0, 1, 1, 0, 1, 0, 0, 0, 0, 1, 1. Okay, let's pay attention to what happened. So these was our pivot, 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 and pivot. When some entry is a pivot, everything below and above it has been turned into 0. So that's a major achievement. Now we insist on one final thing to have a unique answer, which is the following. All of our pivots have to be exactly 1. Well, 3 of them by accident, they were just ones anyway. This is only odd man out. We are going to convert that one also into a 1. So I'll have -R2. Out comes my final answer, which is 1, 0, 0, -2, -12, 0, 1, 0, 1, 6, 0, 0, 1, 1. I forgot my zeros here. 0, 0, 0, 0, 1, 1. So let's again look at what we have here. This was the right hand side. None of them ever become a pivot, nor do we try to intentionally eliminate any of them. That's just on the right hand side. On the left hand side, these were the pivots. They have been all turned into 1. Everything above and below them has been turned into zeros. This is 0, 0, 0, 0, 0, 0. Well, to see our achievement, we better write this thing as a system when we'll see what we have achieved. Before I get to that stage of writing it, this has a name to itself. It's called the reduced row echelon. Form. So reduced row echelon form. Pivots are 1. Above and below the pivots, everything has been turned into 0. This is a unique result for any matrix that you start with. Now, if we go ahead and write the reduced row echelon form, we see what's the significance of it. So this was x. So this was x, y, z. What was this thing? U, W. So that reads x minus 2u is equal to minus 12. Next one reads x plus u is equal to 6. Next one reads z plus u is equal to 1, and next one reads w is equal to 1. So what do you think we should do with this thing? What we do is that the variable that's not associated with one of our pivots, that one is going to be declared as a parameter or a free variable, and we might as well take it to the right hand side. So we take this odd man out that is here. We do the following: we call u a parameter, sometimes we refer to it as a free variable. Free in the sense that this value u can be any number it wants to be, and then x, y, z are going to be decided based on that. Let's go ahead and write this thing. See how does it my equation look like. My equation is going to read like minus 12 plus 2u, y is going to 6 minus u, z is going to be 1 minus u, and w is going to be, well, w is just 1. Now in your textbook it insists that the parameters, we designate them with some special letters. Typically they keep T and S and such for that. Any letter other than the ones that you're using here is fine. So to follow the tradition in the text, I have one free parameter here. I might call this one as my T. So with that in mind, I go ahead and write my answer in the following style. I say x is minus 12 plus 2. Instead of u, just to follow the book's tradition, we just write t. Y becomes 6 minus t. Z becomes 1 minus t. And now we bring u in the mix as well. Write these things in order. U becomes just t itself. This is the same thing. And w is just 1. That is our solution. So when the textbook asks for solution, x, y, z, u, w is equal to, we have a constant set of numbers, minus 12, 6, 1, 0, and 1. And then we factor a t out of the rest of them, and we have 2, minus 1, minus 1, 1, and 0. So here's our solution. What does it look like? Well, based on what we have talked about at the beginning of semester, this looks like an equation of a line. Equation of a line where this is a 5-dimensional word, as x, y, z, u, w in it, 5 variables. Here's some starting point. Somewhere in that space we have some point, and then we have some direction vector. So this is like a r0, and this was previously we referred to as a d or a t or a v or something. So judging from what we have done before, this is the equation of a line. In R5, in a 5-dimensional world. In that line, this will be some sort of a starting point, and this one will be our direction vector. Okay, this was a bit tedious, I'm sorry. There is nothing that can be done. We try to prepare your mind for it. We do have lots of numbers to deal with, so we went through an example, a rather extensive example, but for the next time I will give you access to some helpful software that's going to take some of this burden off of you, but it was important to learn what is really going on. So let's go back and see what we learned. We learned about matrices, where the matrices come from. We said we are aiming for triangular matrices. We don't get them, but we do get row echelon form. When we talked about the row echelon form, it was important to have an entire rows of zeros at the very bottom of the matrix. All the other rows have a so-called leading entry, which is the first non-zero entry of that row, and leading entry of each row has to be to the left of the one below it. So let me just remind you again, we had these examples here. So these are the leading entries, non-zero, first non-zero entry. As you go down, you have to go to the right. Sometimes you go right 2 steps, sometimes 3 steps, and that is why your triangle gets to be not like a perfect triangle. It looks crooked or whatever it is. That's the idea of an echelon. So we looked at that. Here was another example of the same thing. Again, these numbers are marching toward the right. That is what makes the echelon form. So we understood what is echelon. So we want to solve a linear system. We aim for the row echelon form. At the beginning, it is not in row echelon form. What do? We have elementary row operations. Elementary row operations, there were 3 types of them. The most important one was take a row, let's call it row I, multiply it by some number and add it to some other row. That was the addition operation. You're adding something to something else. Sometimes, for nicety's sakes, you take 2 rows and exchange them. So this was the exchange operation. And sometimes you just multiply a row by a number to clean the denominators or divide by something and so on. So this was the multiplication operation. The 3 of them together are referred to as elementary row operations. Every time you do one of these things, you're just taking one simple atomic operation, carrying it out. When you do that, the matrices you create are called to be row equivalent. So for example, when I started this problem way up here, every time I'm doing some operation to them, all of these are going to be called equivalent to each other. So we have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 matrices. These are all equivalent to each other. One of the rather tough problems is how do you know 2 matrices are row equivalent? And the essentially only way to handle it is reduce both of them to reduced row echelon form. If they are survived by the same matrix, then they are equivalent to each other. So we have the idea of equivalence. The way we approached our problem, we have 2 choices. Do the Gaussian elimination, make our echelon and do back substitution, or do Gauss-Jordan elimination, which is one single approach from beginning to end of the problem. We have the idea of a leading variable versus free variable. Let me go ahead and explain that in this context. So free variable is the variable that does not associate with a pivot. That becomes a free variable. That's the item that's taken to the right hand side and a parameter is assigned to it. So when you make your echelon form, the variables that associate to the leading entry, they are going to be called dependent variables. For example, here x, y, z, w are going to be dependent, meaning what? X depends on u, y depends on u, z depends on u. In this case, w doesn't. That's fine. The variables that are going to be taken to the right hand side, they are referred to as free variables. So here we might as well also note that everybody that's left, x, y, z, w, are called dependent variables. That is, when u goes to the right hand side, they will become dependent on u. This one, of course, if you want to insist, is plus 0 times u, so it is dependence. You can think about it as a weak dependence. Okay, so we talked about that one as well. And next time we are going to talk about the rank of a matrix, a rank theorem, and we have additional material to talk about in terms of homogeneous systems. But to prevent this thing from becoming super long, let's postpone that to the next time. So again, sorry that it is a bit tedious, but as I said, we are going to have a bit of a remedy for that. It's the bread and butter of linear algebra is Gaussian elimination or Gauss-Jordan elimination. That pretty much every problem revolves around this operation. So there's nothing we can do about that. It's the basic tool of this course is Gaussian elimination. So let's make sure we learn that, and then we are going to continue with our lecture next time. Until then, good luck and God bless.